I really appreciate your attention to everything tonight. I'm actually losing my voice. That's good. For our final team tonight,
Should I just record
we
it for
give you
them?
team Screwy.
I'll just record their project.
Hi, I'm Michael Baurley, and I'm the project lead and build lead.
Hi, I'm David Purlowin, and I'm the task manager at Trello and the technological lead.
My name is Diaz, and I'm the communications and documentation lead.
My name is Ben Korkis, and I am the research and design lead. Our faculty advisor this year was Mr. Jeff Green. He led us through our design process. And Mr. Manier was our mentor, and he guided us as well through our design process and gave us multiple points of great advice.
Define the problem.
So this is our timeline for the research. The main things this goes over is the beginning process, which is the justification of our problem, the IPE, so finding out who already followed the problem, a business plan, a timeline, and figuring out who our mentor is.
As Vex Robotics students, we knew that, for our problem statement, since we all participate in Vex Robotics, we all came to the same conclusion that sorting Vex parts is a very time-consuming and laborious process. According to a survey that from 56 respondents from Vex students and teachers, we came to the conclusion it took on average 2 people 2 hours a month to manually sort all their Vex parts, which is 4 hours a month that could be spent on other tasks. As we mentioned, our team created many surveys that we sent out to Vex Robotics students, teachers, coaches, competitors, and lobbyists nationally to gain their input on the problem, and these were the results that we obtained from those surveys. So the first one asked the question of, did they find sorting the Vex parts time-consuming, with an overwhelming 91% saying yes. How many people did they assign this job? 39% on average had 2 people doing the sorting process for this. For how many hours did it take to sort all this? They once again came to the conclusion that it was on average 2 hours with the total 30% of the population. Do you enjoy sorting Vex parts? 61% said a resounding no, as it was very obnoxious and time consuming. What is their current method of organization? 75% use small bins. These bins are provided by the schools that these Vex Robotics teams compete in, as they are just the simplest way to sort parts due to their large quantity and easy to purchase. What is the most frustrating thing about this entire process? 33% responded that it was time consuming, whereas another 33% claimed that after they were done organizing, within a week, all their progress was just messed up as a result of the building process that comes with robotics. What was a price point that people wanted? 33% wanted at least $10 to $25, whereas another 33% were looking to $30 to $45. And this leads us to our connected organizations for this problem. As you can see on the slideshow, these are all the organizations that have some sort of involvement with Vex, whether they're the ones hosting the competitions, providing the parts, or even giving us the CAD sketches that we use for this problem.
Our goal was to make an automatic organization system to separate all of the small parts based on the part size and the actual part. Our goal is to have all the parts sorted within 10 to 15 minutes automatically.
So this is where we generated our concepts. This is the timeline. This includes things like our concept sketches, our design matrices, our CAD, our filament research for 3D prints, and our overall goals.
These were the current sorting methods that we found just in our research. They were either too big, too expensive, or too DIY to mass produce for the Vex competitors.
And then we had our patent research. So as you can see, we found a large list of different kinds of sorters. However, an issue with it is that most of them were not at all related to screws, and those that were not specialized towards Vex, and many, if not all of them, use expensive and complicated parts, which are not very good.
Concept sketches 1, magnetic separator. Idea 1.1 is for a magnetic lid to screw on a container with the parts and attract all the metal parts. Idea 2, magnetic guide. This system's idea was to have a magnet on a vertical slider with you pouring out the non-magnetic parts into their respective sorting system and do the same for the magnetic parts. Idea 1.2, CAD. Idea 1.3, magnetic conveyor. The idea for this design was to pour out all the parts onto a conveyor with a magnet inside of the conveyor, so the conveyor would spin around with the magnetic parts attached to the conveyor, and then they would eventually drop off. Idea 1.3, CADed sketch. Idea 1.4, magnetic sweeper. The concept of this sketch was similar to idea 1.1, but instead the magnet would be stationary. You would pour the parts in, then pour out the non-magnetic parts, and then sweep out the non-magnetic or the magnetic parts into the next system. Idea 1.4, CAD. Concept sketches. 2, screw sorter. Idea 2.1, screw spiral. The way the system works is the screw is guided and rolls down the spiral, falling into their respective bin based on their size. Idea 2.1, CAD. Idea 2.2, screw stairs. This idea was modeled after raised screw sorter that we found online, a vertical version of the screw spiral.
And then our third portion, the metallic sorter. So for this hole-in-the-wall idea, we had an idea where it was very much like the Mechanos screw nut sorter, which was one of the 3 sorters we found on YouTube. And essentially the wall code would change based on what cross-section you wanted to remove. So for instance, if it was the nuts that you wanted to remove, you would open the cross-section that would only allow for nuts to remove, and the rest would remain in the spinner. The second idea was the funnel slant, which essentially had a track that all of the items would fall into, and then as they go down the track, the hole would widen slowly, allowing for the smallest of the parts to fall through first, and then the larger ones falling off later on, and they'd each go into their respective bins. And then we have the spacer sorter, which was the non-magnetic parts. First we had the sieve and sort, which sorted the biggest ones off first and the smallest last, having a wall hanging down from the top of the mechanism, where as they go down a slide, the taller ones will get knocked off to the side and go into bins, and the shorter ones will pass right underneath. The size slide, our other idea, was removing the smaller ones first by having small cross sections that fit the smallest of the spacers on the floor, and then those that were bigger would simply roll over. And this was the CAD for the idea.
So here we started to develop our solution. For the solution, we came up with the criteria. The top criteria we found were the performance and accuracy, autonomy, ease of use, safety, service life, service and weight, and sorting speed. We made a tier list of all this, everything from up to down, left to right. So top left, which is customer needs, which is top priority, and then the accuracy and performance, and etc. With aesthetics being the least important thing on a design. This was our design matrix for the magnetic separator, the magnetic conveyor 1. For the screw sorter, the screw spiral 1. The metallic sorter, the funnel slant 1. And then the spacer sorter, the size slide 1.
Then we researched some filament because we intended to 3D print all of these parts, and so we needed to know which one would fit our needs the best. And our printer was capable of printing the PLA, ABS, TPU, and PETG as filament options. And the issues we found with each is that PLA has low durability, however it is cheap and prints well with the printer that we have. ABS is also cheap, but its main issue is that it releases toxic fumes when you 3D print it. So in a closed environment, it's toxic to humans, which is not very user-friendly.
How'd you use it normally?
TPU is a rubbery substance, so when it wouldn't really be very effective for what we were trying to accomplish. And PETG was durable, slightly less cheap, but very similar to PLA.
So on your screen is the bill of materials that we decided that we would need for this process, which would consist of 1 kilogram of spool of PETG for 3D printing IDs 2 through 4, 12 neodymium magnets, a 6 by 18 inch 22 gauge sheet metal, and a VEX V5 motor were all the parts that would consist for our conveyor belt design. And then the tools and equipment that we would be using, which is an Ender 3D Pro and an angular grinder, which were both provided for us in our laboratory. Ender 3D Pro would be used to 3D print the ideas with the PETG filament, whereas the angular grinder would be used to cut the sheet metal that would be needed for the conveyor belt.
Build a solution. This was our printed version of the spacer sorter. We had 2 iterations due to the angle needing to be increased. It did not work very well, so we decided to move on to different ideas. These are our prototypes for the screw sorter. The image on the top left portion is the first prototype and needed to have a lip added to the interior of the screw head guide. The top middle is the small scale prototype with the lip, which did work. So then we decided to print in PETG to test the quality, but we found out the quality came out bad on the Ender 3 Pro. So we decided to keep on doing PLA for our prototypes in the future. And then the image on the right is the full scale prototype with the lip. Test the solution.
So this is the timeline for the test solution, including things like printing the actual things and creating the test plan that would use to test the actual product.
So this is our testing plan criteria on the screen, and the whole synopsis of our testing plan criteria is that when we would pour a bin of VEX parts into our fully automated system, each group of parts should spend almost 20 seconds in each system and be sorted with a 95% accuracy per each system. That way it combines both efficiency and accuracy when sorting the parts.
And so we reached a point where we didn't have all of our prototypes necessarily 3D printed, and we were coming close to December. And then we talked to Mr. Munir, our mentor, and he told us some very wise advice. We needed to either choose to specialize in one very important part or be very mediocre in all of the parts. And so we specialized in screws, and we redefined the problem.
New define the problem.
So this is our new timeline. First, we had to start redoing the CAD, as all our CAD was designed for everything. We had to start specializing it for specifically screws. Then practice presenting, as the time we were starting to run out of time, so we wanted to start working on that. Just a prototyping, starting working on the board, and our mentor approval of our final.
So our revised problem statement is that VEX Robotics teachers and students have to take time and manpower to organize their screws. We did some research of our own since we had surveys, but the results were unfortunately lost when we went to our Ohio competition as we were traveling back. So since we were running out of time, we decided to conduct our own test, which consisted of, as I will pass out soon to you judges, it was 120 screws, 12 different sizes, so 10 screws per 12 sizes. And we each took our time sorting them, and we got an average of 9 minutes and 32 seconds to sort.
And the justification, we took 10 of each screw length except for the 2.25 inch due to our accessibility issues. We unfortunately did not have those available in our lab. So we used what we had available, and they were mixed together in that bin and dumped out onto a table, and we timed ourselves for our sorting speeds. So we had our times. They averaged out to 9 minutes and 32 seconds. it's worth noting that Michael, Nick, and myself
names on this
are
one.
builders in our Vex
Michael
robotics
on the board.
teams, so we have worked with screws a lot. And I was the one who put those screws together the day before we did this test, so I did have some very recent experience with doing it, and David is a coder, so he doesn't have a lot of experience working with all the screws. So that may explain his time, and also it should be worth mentioning that it took me about 90.
Sorry.
Once we had this bowl, well, once we had this idea and problem, we needed a way to input that would only require screws to go in, right? But the thing is that I didn't know necessarily how to describe this because I just had an idea of a singular bottom point, and no matter where it's sitting, on any surface of the bowl, it would fall to the bottom. And so there was, the best way I could describe it, it was a banana. Specifically, the very bottom point. Because if you look on both sides, where the arrows are pointing, it's the very bottom. And it's not flat on either side. And this was the best example I could come up with. And so I pitched my team the bowl, which they deemed the banana idea. Yeah. And this was how it came out. This was the prototype. And then the slide CAD. So essentially, the next part of this was after it fell through the bowl, it needed to go into a slide very similar to the track idea from the funnel slide. And it would go down with all the threads hanging down and the screw heads on top, so that way they'd all be in the same orientation. And then at the end, there is a twist which allows it to rotate to the side, which would fit with the screw slide functionality. And we put them together in a CAD, and this is how it looked. And I must note, this is how several of about 14 different iterations looked and printed. It was.
So this is our V2 RAM prototype CAD. We decided to make the path to be more linear than circular in a helix shape. This prototype will allow for easy storage and fix the problem with the screws falling out of the system. These are the bins for the RAM prototype. They come in 3 different sizes due to sizing issues, and they have an incline on top of them to prevent clogs in the system. These are the CAD renders of the prototype that I made, and they were unintentionally starburst colored. New build solution.
So we are about to introduce our final iterations for this process.
Ramp and bin 3D printed prototypes. The printed quality on this was amazing and seemingly handled the base level of testing. The results of the full-scale test will be revealed later on.
These were the great many iterations that were shown. And those are counted up to 12. However, I should note that the bowls were not included, and this was 3 separate prints. So yeah, it was a lot of iterations, but the changes were that there was the track width, the angle of the walls, even on some of them curving the walls, curving the track. There were a lot of different ideas that were implemented and ultimately did not succeed. So at the end, we pivoted and decided, what if we used a different idea that wasn't exactly the same? And it was somewhat inspired by the screw spiral exit itself. Is the video playing up there, or is it just sound? Okay. So the video there, essentially the screws go around, and because it's a spiral, and there's an incline towards the outside, what happens is that the screw threads naturally fall into the sides, which makes it much easier, and this was the total CAD of it all.
As we were running out of time, we came up with a second idea just in case to work at the same time. This idea was kind of a screw lifter, where it was a bin with incline down, and at the bottom of that incline there was like a linear pusher that pushed. I was kind of bad at sketching this, I'm not gonna lie, but there's a linear pusher that pushed up, and it would hold like one, maybe two screws in it, which would push it like at an angle like this, which then would make it fall into a hole and get the screw bottom aligned to thing. Here's a CAD thing. It's kind of hard to tell what it looks like without the other part. There was another part which I was going to use, I believe it's called a Scotch yoke system. I didn't get too much into it as I did run out of time, but it was basically a system how I was going to do a linear pusher using a VEX motor, as we're selling this to people who use VEX. So we figured they would have at least a VEX motor and a VEX shaft. So we were going to make our own type of gear system to help make the linear pusher. And then here's the design matrix, the spiral shifter 1. And then these are just like a top and ISO view of both the things printed.
So here we're gonna do our final test solution, and similarly to our first testing plan criteria of sorting, but now instead of multiple parts, it's just screws. We still wanted to aim for 95% accuracy, as we believed that we wanted this to be fully autonomous with little error. We also wanted it to get into the orientation before the ramp. We wanted that to be 95% accurate as well, just to improve the efficiency. And we also wanted to make it easy to use, because sorting screws can be very time consuming and painful. And I don't think making this process any more difficult is going to benefit our customers or corporations who would be looking into this product. And these were the results that we conducted.
It's worth noting that we were not able to get any confidently good results from this prototype, as it was printed this week, and unfortunately due to some printing issues and a bit of unforeseen design error at the very bottom of the slide, the screws get caught right before falling in, and the larger, about 2-inch screws is where it starts to get a problem. Do not actually go into the track if they're inserted upside down. So a design improvement could be that it could be widened in radius.
That being said, we were still able to test the screw slide through manual input, and through this, I did 4 different tests, grabbing a random amount of screws, measuring them, and putting them in. If you look there, you can see the input and output. The output is how much screws actually got into the correct hole. All of them did get into the correct hole with the size they're supposed to be. And then this is learning moments and future endeavors. In terms of future endeavors, I want to talk about who would we be selling this to. This would be sold to niche specific users, just as in only people using VEX, i.e. people who do the VEX robotics. PLTW also uses VEX parts, so it would also be sold specifically to VEX PLTW too, and schools, anyone that's just that uses VEX in general.
The main thing that I learned was that even though we worked on this for the past 7 months straight and we never really took any breaks, we were unable to get the system to be fully automatic. Even though we followed the design process best as we could, we just kept on hitting roadblock after roadblock with the input system that led the system to being unable to be automatic. So the main thing that we learned was the engineering design process doesn't necessarily lead you to a complete solution, it can lead you to a solution.
One thing I really learned similar to that is the iterative process of engineering, which is iteration after iteration when it seemingly should work and then suddenly it doesn't. It doesn't work, and you have to sit down, figure out why, go back to the drawing board, make a few changes, run it again, and again, 15 times. But it's effective.
One of the things that I learned was understanding time constraints and realizing that you can't have a fully functional product done in one whole school year. As you saw with our original goal, we had this whole elaborate system to sort a ton of VEX parts. And even though we condensed it to just one part, we were still unable to finish it due to iterative process and time results. I had a conversation with Mr. Green, like, this is rough, man. Like, we've gone through 15, we have as many bins on that slide as we do iterations of that input thing. Like, what's going on? He's like, you realize that the whole point of this project was to learn the design process. It wasn't meant to have a fully finished product. And I'm like, you know what, you're right. Even though it didn't turn out as we wanted, this was still a very good learning experience for us. And even though there's still modifications that could be made, it is a very good position that we have found ourselves in for this completion of the product.
Yeah, the animation.
Any questions?
I need the background from the car.
Yeah.
How do I leave?
No, I truly applaud.
keys, I can
The
just
word
run.
just came to mind, and everybody's probably pretty tired and burned out, and you included. So I applaud that, and the word is perseverance. I mean, that just sums it up, right? And my second point is going to be a little plug. This is probably one of the reasons why I became a civil engineer and not a mechanical engineer.
All right, I'll try to keep it short for you guys. Who came up with the idea?
Which idea?
Let me rephrase that. Yeah, it was slightly confusing in the beginning because you had the magnetic sorters and you had the size sorters, and it was like you guys kind of, your whole idea was way too far out there. And a sage professor told you to edit it down and come up with a good idea instead of a lot that are bad. That will serve you well in the future to remember that. Super important. The other thing was you've got logos on your brochure.
Yeah, so
Talk to me.
we heard your feedback with one of the earlier teams, with the gym team, and then we were all saying like, oh crap, we didn't really reach out to these organizations saying, hey, could we like maybe use your logos for brochures? But that, Mr. HS, sorry, but that is something that we would consider in the future, to reach out to these organizations to present this product. Even though they are connected organizations, I feel like each one of them has the right mind as to why they should get this product, whether they are the suppliers, the ones making the games, or the ones hosting it. So that is a very good consideration to take into the future.
You said you lost a survey when you were, what survey did you lose? Can you repeat that?
So when on our robotics team, we went to a signature event trip to Cleveland, Ohio, and we competed against many top competitive teams.
And how did you do?
There. Not very well. We did not do very well. However, I will say that I went around to the teams and asked them questions and wrote down answers such as, would you find a screw sorter useful? Are your screws sorted? How long does it take you to do that? And we got some results, and the only one that I can confidently say I recall for certain is that the price area that they were willing to pay was generally around $50. That was what most people said. I would pay $50 for such a product that only sorts screws.
And based on that, where would you come in price-wise with your current concept?
I would say around 45 to 50, so they were pretty accurate with what we wanted. To print the whole thing, we averaged around $20, and that's only including the actual print itself. Then there's also other things like you gotta make sure you have the screws, you gotta make sure you have the motors and stuff. So I would say around $50, just because there's also the print time and the amount of, we only have a limited amount of filament and printers. And also in one of our first surveys, we did ask the same question, although this was for overall sorting. The average price range was people said 10, which I don't know why they would say that for something like this, but 10 to around 50, because there was like we had like a 10 to 25 range and like a 25 to like 45 range, and they were both tied, so I'm gonna say 10 to 50 was the average range of what people would be willing to pay for this.
Great job, guys. I want to share some things, what I call the soft skills of engineering. So you guys have a lot of good experience here with this process here that I can hit on that are very real world things. Don't take any offense to any comments I make, just it's part of the learning process and we're all on that walk, right? So I know you guys appreciate some transparency here. So one of the things I realized, so there's nothing like schedule pressure to inspire innovation. So you guys experienced that, right? We're running out of time, and all of a sudden more and more ideas came to fruition, right? And then you kind of kept going down that rabbit hole. So, you know, the downside of the result of all that, though, is another real thing that happens in life is you ran out of schedule. The project had to end, and then when you really needed it to end, then you had equipment problems, so construction delays further complicated the process. So like in the end, when an owner or, you know, the government agency is paying you hundreds of thousands or millions of dollars and then you don't deliver, that's a tough reality that it's hard to move on past. But you know, the learning process is here for you guys. So I think you did a great job. I know all of you are going to be really good engineers one day. You got it written all over you. One of the good things on that soft side that I mentioned, like I can't highlight how important it is when you're in the work world on a team like this, is having fun with the people that you're working with. Like that's what makes a good team. And you guys obviously had fun working together, so that was a really good thing, right? That's you can't, like, that's one of those things that when you're in office you can't put a price on, and it can make or break a team success, right? So good job. And then touching on the perseverance and the commitment, like you guys in it to win it, right? No matter what happens, we're working together, we're gonna solve it. Last thing I'll touch on that's another soft skill is communication. Like one of the biggest parts of my job is being able to communicate all these ideas, all these solutions, all these problems, communicate them to non-technical people, right? Like everybody sitting in the room. So, and this is just some tips on the presentation. Like, so you had all the information there, but you also went through it really, really fast with very little explanation. So like, it was all there and you had it, but you gotta like slow down, speak in non-technical terms, relate to everybody, and let them digest the information. Because you guys know it, your brains are running 1,000 miles an hour, right? So you think, I said it, well, move on to the next. But everybody here, we're like way back on lap 4, they're on lap 30, you know what I mean? So just slow down when you're presenting information.
I would like to mention that this slideshow was 87 total slides. And we were told, hey, 20 minutes to do this whole thing. And I did a presentation earlier this week where I had 20 minutes for 35 slides.
Yeah.
So if there was any sort of confusion as to why things were cut short, or if we didn't fully flush out ideas as the guy who made the presentation, it was because as I was talking to Mr. Green about it, he said, I was considering, hey, should we cut this in half, like what we actually did at the main point of the project, or should we go through the whole design process? He said, go for the whole design process, because at the end of the day, that's what the project's about. And I think that is one of our biggest constraints with this presentation, is because there were so many slides and we were given such a short time window. I mean, even though we are going over throughout all the presentations, it doesn't matter as much, but if we were supposed to hit that 20-minute window, there was really no way for us to consistently fully explain every part of our process, because if we did, we might be here for another 30 minutes.
Right. So you just hit on the point exactly, right? In the real world, the time is often one of the most critical factors. So hitting that 20-minute mark, like you have to tailor your presentation and to make sure you land the plane in the 20 minutes, right? And I always think when I give presentations, what's on the board is only an aid to what I'm saying. And my message, my words is what is most important. So just think of that, like that's just a tool, but really what's coming out of here in these words, that's what you want to make sure gets clearly understood. So good job. Good job.
Thank you. It's not my fault.
Yeah, I take full credit for any failures at all. Yes,
We still love
I
you.
was.
Failures.
Anyway, you guys are great. I love watching you up here, and just the energy was like, I mean, the design process 43B. Just could have been like a Saturday Night Live sketch or something. So just so fun. I will definitely just totally, just agree completely with the communication stuff. That's just really wonderful advice. And if I can, with the risk of just complete failure, can you demonstrate the spiral thing real quick? Just putting a few screws in there just to show the audience
With pleasure.
what actually happens.
Let's go back.
You'll be able to see it in the video. I can't
Go,
see it any
man.
further.
It reaches there, it gets stuck at that point. Then placing a larger one at the bottom, I'll turn it, it gets stuck right here.
Place some shorter ones. Take those out. 10. Just make some guy.
On that too, you said the shorter ones work, so that's what we're looking for.
Ben, we talked about this. There you go. Nice.
Revise that problem statement, Mike. Small screws.
But he just moved it.
Excellent. I'm going to give you a round of applause right now. Good job. Good job.
Yeah.
Okay. You can stop. That was really good.
Ben,
So
you listen to
the slide sorter works, which you showed us in the slide, but you could have potentially showed us in person. I know it's tough because it's like we can't really see it, but that's something you could have showed us, and you could have showed us that even though it wasn't perfect, it still almost works. I mean, right now I'm looking at it, I'm like, oh, that's like a simple thing. Like the next print, they're just gonna nail that, and that'll work. So it's not like, oh, this thing just doesn't work, which wasn't 100% clear. And just to kind of like add on to what you're saying, like the communication aspect, and also don't sell yourself short. Like you were really, really, really close. This was not an abject failure. And remember, it's like, there are gonna be a million critics in the room. There are gonna be a million people that are gonna be like, you're not good enough, you're not smart enough, you're not whatever enough, I'm so much better, I have a better idea already. Like, you're gonna find rooms full of critics. You can be your best cheerleader champion. We did this, we can do this, we're so close, and all we need is another $1 million. And we're gonna get So just really great job, it was so much fun, and great job, guys, great job.
Thank you.
So I love the creativity. I think you guys did do a pretty awesome job, but I think your biggest constraint was time, and your solution was in your deck. It's called the project timeline. If you use the project timeline for what it's for, it's, hey, we're gonna design, we're gonna build, we're gonna test, we're gonna deploy, right? Whatever phases you want to break down. And so if you're in design and you're 2 weeks overdue, it's like, guys, we got a problem. But we should have known that like in October, right? Because I heard you say adjust, and adjust is exactly the thing. We just want to learn to adjust earlier in the process. But I love the creativity. I mean, you guys aren't professional engineers, so don't beat yourself up. I think what you learned from experience is a whole lot better than what we could tell you, like verbally. So keep going. I think it's cool. I think it's creative. I think any Vex person would be like, wow, I would love to see that thing work, right?
Yes.
So good job.
Almost.
Yeah, it's a Vex project. I have to say something. So, first off, guys, you guys literally put together like a whole design book, basically in these slides. Like, some of us may understand the time it takes just to even make these CAD simulations. Nonetheless, you got to think about tolerances, like how exactly it's going to work. You got to think about that curvature in the screw head to make sure it's not going to, like, you guys have to think about a lot. And I don't even have a question, more so just, hey, the skills you guys have learned from Vex and from this is going to pay dividends in your future, and I'm excited to see where you guys go. So, good job, guys.
Thank you.
Oh my gosh. Oh, it's misprint. Okay. Yeah, never mind. We're all good.
I'd like to thank you panel members for coming. Your time is very valuable.
What?
And giving it to us is very much appreciated. Family and friends, it's been a wonderful night. I would offer you desserts, but we have teenagers in the room, so there are no more desserts. Thank you for coming out. You're welcome to leave, talk, stay.
Yeah. Great job.